In our second section of our Chapter 2, Organic Chemistry, we're going to look at polar covalent bonds and the distribution of the electrons over the entire molecule, as well as in between two atoms sharing a pair of electrons. So we'll revisit the term electronegative. From there, we'll talk about polar covalent bonds and a dipole moment. We'll define the term functional group in preparation for your group work, and then recognize the polarity of when we look at something known as an electrostatic potential, such as these models right here on our page. We can see the more colorful that the model is, the more polar that the molecule is as well. The electron distribution in the red region is very rich. The electron distribution in the blues and the greens is very deficient. We can see that this molecule is indeed polar because of the electron distribution being unequal, that the distribution of electrons is being pulled to the top of the molecule. When I look at a compound called LiH, lithium hydride, the very rich electron-dense regions over here, where I see a high amount of red, tells us that the electron distribution is being pulled in the right direction. So we have a deficient area where we see the deeper colors, and the brighter colors represent where it would be an electron rich. Now notice here, this is completely the same color throughout. An equal distribution means that it's a nonpolar molecule. And here we see a rainbow of colors where the reds indicate electron rich and the blues to greens indicate an electron deficient area. So generally speaking, molecules can be polar or nonpolar, and so can the bonds based on the electronegativity difference between the two atoms. So the second topic, polar covalent bonds, begins with a reminder about another category called the ionic bond. Remember, ionic bonds are formed by a complete transfer of the electrons. So it's incorrect to describe polarity of an ionic bond. They're not sharing at all. We ended up having an ion form where a complete transfer of an electron. Here, you just take it. I'm done with it. So ionic bonds are not part of the lesson, salts, if you will, but we're looking at the overlapping of orbitals between a nonmetal to a nonmetal, where we see that the distribution between the two nuclei of the atoms either being an equal sharing or one of them has a tighter hold, bringing the electron density towards itself, making it a polar bond. So just make sure we're understanding that we're only focusing on shared pairs. And to determine the polarity of the bond, we know that we just simply look at electronegativity differences. We discussed this a little bit earlier in prior lessons, saying that fluorine is the strongest of strong nonmetals, the most electronegative element, with a value on an electronegativity scale given as 4.00. The least electronegative element is cesium, the opposite side. This is the most active metal. Therefore, it does not want to attract electrons. It wants to get rid of electrons. So it has the lowest number on the periodic table for electronegativity, assigned as 0.7. So the electronegativity increases the closer you become to fluorine. So when we look at the electronegativity difference between two atoms that are bonding, we can find out on the scale what type of bond exists. If the differences exist between two bonds and they are not large, so it means if you take the difference and not large means greater than 2.0, the electron's not shared equally. So remember, if it's greater than 2.00, you're looking at something called an ionic bond. I did that again. So when I subtract an ionic bond, let's say for lithium fluoride from that previous picture, fluorine has an assigned value of 4.0, lithium has an assigned value of 1.0, so the electronegativity difference is 3.0. That's greater than 2. This would be known as an ionic bond. So electronegativity, that ability to attract in a covalent bond, we need the differences to be below 2.00 to even consider it to be covalent. When we think about unequal sharing, we need kind of a way of showing who's in charge of the electrons. I'm just going to back up a moment to this particular slide. Remember that if it's a difference of electronegativity difference, if it's a 0 to, let's say, around 0.3, we would call that nonpolar, which means it's an equal sharing of electrons. And let's say greater than 0.3, but less than 2.0, kind of in that range, that's where we're looking at the polarity of a bond. Someone's in charge of that electron distribution based on its stronger pull based on the electronegativity of the atom. So if I had a carbon-carbon single bond, we would say that that's an equal sharing because the electronegativity difference between two carbon atoms, because they're alike, the electronegativity difference would be equal to 0, nonpolar. If carbon is assigned a value of 2.5, oxygen is assigned a value of 3.5, I take the difference between those two and I find a value that would indicate a polar bond. And therefore, the more electronegative element has the distribution of charge surrounding it. Remember, these oxygens have all kinds of dots around them as well, not shown, but we know they're there. So this partial negative region reminds us that the electrons are being surrounded around the oxygen, and carbon is left as a little bit positive. And you'll see this as an arrow showing the positive region in carbon pointing towards a more electronegative element called oxygen, a polar covalent bond. You can see how we use this arrow to show the direction of the electron distribution. The arrow often is used a little positive sign. Make sure you just remember to point to the more electronegative element. Now this is worth mentioning here. I know that a carbon-hydrogen bond is termed as a nonpolar bond. Even though if I subtract these two, I get a 0.4. In organic chemistry, CH bonds are uninteresting, so they're always termed as nonpolar. So just kind of remember that, CH nonpolar. But, we're just doing a little subtraction to get the idea of the degree of polarity. The more electronegative element will pull the electron distribution towards itself. So we'll take a hydrogen and a chlorine, knowing that chlorine is more electronegative, it's closer to fluorine, and we simply draw the dipole moment. That tells me use the arrow to show the direction of the distribution of charge. The dipole moment here would lie with the chlorine, the more electronegative element. With IBr, who's closer to fluorine, is the bromine, making iodine, as we draw its vector quantity, the dipole moment, distribution of charge would be closer to that of bromine. Of course, with two like atoms, we don't draw anything because there is no electron distribution that would be unequal. So FF, it would be inappropriate to actually draw a vector diagram. Here's an example from our homework. It says, analyze the polarity of each bond in the following organic compound. So we have a structure with two carbons. We have a halogen, chlorine, and an oxygen onto second carbon. We have two hydrogens and a halogen on the first carbon. So which bond, other than the CC bond, because CC would have a dipole moment of absolutely 0, what other bond is the least polar in the molecule? When I read least polar, you're looking at an equal distribution of electron density between the two atoms. And remember a moment ago I mentioned CH bonds are considered nonpolar. So when I subtract, I get a value right on the edge, and we always remember as organic chemists that nonpolar CH bonds exist. So, all right, that's fine. That one's the least nonpolar, or the least polar, most nonpolar. Which carbon atom has the most partial positive charge? So what we're being asked here is, considering what's attached to the carbons, who's pulling the electron density furthest away? Well, with carbon 1, the only vector quantity we have is the distribution of charge towards the chlorine. That's a polar bond. But C's and H, they're not really unequal at all. Here we have two more electronegative elements pulling the electron distribution in either direction, making this carbon more positive than the first carbon. There are two very electronegative elements pulling carbon's electrons from it. So the right carbon would have a more partial positive because there are two atoms vying for its electrons. And so let's take that step to talk about molecules. So in the third section of our chapter, we take a look at the entire electron distribution over the entire compound to decide, is it polar or nonpolar? And that's really what I started this lesson with, is looking at those maps to decide. Your section will start out by a calculation called a dipole moment. The unequal distribution of charge can actually be calculated with a formula saying how far apart are the charges, so the distance between them, radius, times the charge. Is it a magnitude of +2? Is it a magnitude of +1? Is it a -3? What's the magnitude of charge times the distance between them? And that will find the dipole moment. These dipole moments are expressed in a unit known as debye, which is a coulomb meter in the standard international unit. So it's a derived unit. What I'm telling you is I'm not going to hold you responsible for calculating a dipole moment. Take the math part right out of our text. But instead, I want us to decide the polarity based on a number. The larger the value for the dipole moment, the more polar the molecule is. So if you see a number being reported for debyes, the dipole moment unit, just look at the magnitude of the number to decide which molecule would be more polar than another, but do not worry about calculating. So let me give you an example. On page 61 of your text, you're given a picture where it shows us chloromethane. See the carbon, the hydrogen's coming off, and then the electrons being pulled to the very electronegative element of chlorine. So in a picture, this region would be highly red, more electronegative, and these regions would be kind of in the blue-green range of electron distribution. So the entire molecule has the electrons being pulled to the most electronegative region towards the chlorine. So I can see that it's polar based on symmetry. Chlorine is more electronegative, pulling electrons. It will have a dipole moment. So when I see a number, 1.87, that's telling you the magnitude of polarity. If I had a number for a different molecule, so instead of chlorine, perhaps I had a fluorine. Well, fluorine's more electronegative. I would expect that number to be higher. And if I had a less electronegative number, like for iodine, that's not as electronegative as the higher up halogens, I'd expect this number to be lower. We're only comparing the magnitude of the numbers. I don't want you to worry about calculating them. Molecules containing polar bonds are not necessarily polar as a whole. So for instance, boron trifluoride has very distinct polar bonds. Fluorine is very electronegative. However, if you stand in the center and you look up, you look left, you look right in a trigonal planar format, all three domains are identical. It's a completely symmetrical molecule. That means that it's an equal distribution, therefore a non-polar molecule. Notice 0 Debye. I'm standing in the center of carbon here. I look up, down, left, right. It is an tetrahedral molecular geometry. All 4 domains are bonded, and they're bonded to identical atoms. That means that it's an equal distribution of charge in all directions, a non-polar molecule. The bonds are indeed polar. The distribution of charge is being pulled from carbon, but it's being pulled evenly in all directions to make it a non-polar structure. So when I look at these examples of numbers for Debye units called a dipole moment, notice that this ionic compound has an extremely high dipole moment because it's made of charged ions. So it's not appropriate to call it polar or nonpolar. We need a molecular compound, and everything else on here are nonmetals hooked together, so molecular compounds. We see that, for example, when I draw CH3NO2, we would have a resonance structure there. We have a very polar region attached to a nonpolar region. So we have this very extensive negative region here, and thus I would anticipate a very high polarity. Let's look at the trends for the halogen. We have a chlorine followed by a bromine followed by an iodine. Remember, group 7 are called the halogens. It goes fluorine, chlorine, bromine, iodine. That's an F. Fluorine, chlorine, bromine, iodine. Of course, this is the most electronegative element, so electronegativity is highest with fluorine, then chlorine, bromine, iodine. So here we're comparing that trend. Notice as we go down the column of the halogens, the polarity of the molecule decreases. The numbers are going down. Chlorine has a greater ability to pull electrons towards itself, creating a greater polarity as compared to bromine, and iodine, not so much. The more chlorines you put on a carbon, the lower the polarity. In other words, the carbon itself now has its electrons being pulled away from it. It's polar, but it's being pulled in 3 directions evenly, so it's not as polar as if you had just 2 carbons or just 1 carbon. So notice here's 1 carbon attached. I'm sorry, 1 chlorine attached. The unequal distribution definitely lies here because it's being pulled in 1 direction. So this is a very polar region, a high number. But if I replace 3 hydrogens and put on the halogen, you decrease the polarity because the distribution now is going in more than 1 direction. Here we have some OH bonding, water, methanol, and a carboxylic acid. We can see the trend here. And then, of course, completely symmetrical molecules, 0. So when we think about, is it polar or not, I think symmetry. Here's a hydrogen attached to nitrogen, 3 single bonds, making a molecule called ammonia. Is that polar or nonpolar? Well, clearly I see, standing in the center, I look up, I see an electron pair. I look left, right, and down, I see hydrogens. This is not symmetrical. It has 4 domains, 3 bonded, 1 not. We would call that tetrahedral, what do we call it? Trigonal pyramidal, sorry. Trigonal pyramidal. And therefore, this region is very negative, and the electron distribution is being pulled towards the negative area on the nitrogen. Highly polar, we see it has 1.47 is its dipole moment. Even if you think about methanol, there's CH3OH. That's this compound. It's very polar with this very electron-rich area on the oxygen. Water molecule, HOH, remember its molecular geometry is 4-2-2. It's bent. Because it has these electrons on the oxygen, that's very electron rich, making the hydrogens electron deficient, making this a very polar molecule. More polar so far even than the methanol, because this region over here is nonpolar. Here's the polar region, and so we see that water, just based on it being a smaller molecule, would be more polar than methanol. Which of these molecules are polar? Check all that apply. I'm going to redraw these and kind of think with you a little bit. Let's draw this one. I'm going to draw them a little bit like, here's sulfur. See those dots? Here's the oxygens. Here's the oxygens. Now notice what I've done. There you go. I drew them really with a better molecular geometry. This is a 3-2-1 molecular geometry. See these dots? There's 3 domains. 2 of them are bonded, 1 of them are not. The molecular geometry here is bent, meaning that this exposed electron is an area that is electron rich, and therefore, if I stand in the center, all 3 domains are not identical. That molecule is polar. Let's do that one. CH4, C2CH2Cl2. There, I got it. Because I might be tricked into thinking that that looks pretty symmetrical. But think about molecular geometry. This carbon has 4 domains. All 4 are bonded, 0 are unbonded. We know that that's an sp3 tetrahedral molecule. The carbon is attached to 2 hydrogens, perhaps in the same plane. We know that one of the chlorines would be behind the page. The other would be coming out of the page as we draw the 3-dimensional view of a tetrahedral molecule. So now we can clearly see the chlorines are very electron rich. The hydrogens are very electron deficient. Because if I stand in the center and I look 2 directions and see hydrogen, I look 2 directions and see chlorine, they are not the same in all directions. This is actually a polar molecule. Easier to see when you look at the geometry. This phosphorus is sp3 hybridized, tetrahedral. I can see in terms of the central atom, 4 domains, 3 bonded, 1 non-bonded, that's dash, making the molecule trigonal pyramidal. These electron dots are different than the chlorines in all other directions, making this molecule polar. Carbon dioxide, CO2, in all directions, carbon has 2 domains. 2 of them are bonded, none unbonded, so we know it's a linear molecule. In each direction, there is an equal distribution of pulling on those electrons from carbon, making the molecule perfectly symmetrical. Therefore, it is non-polar. We want to identify the polar bonds and the polarity of the molecule. Polar bonds has to do with electronegativity difference. Carbon to chlorine is an electronegativity difference that lies in a polar range. We have an electron distribution being pulled from the carbon equally in all directions to those chlorines. So the dipole moment exists pulling out. So definitely a polar bond in letter A. However, the molecule with its 4-4-0 tetrahedral geometry, because absolutely all four domains are attached to the exact same element, the distribution of charge being pulled away from the carbon is identical in all directions, so the molecule is non-polar. If we look down at letter C, same molecule, except we have 3 hydrogens replacing those halogens there. I do see a polar bond right there. Carbon to chlorine is a polar bond. And because from the central atom, all 4 domains are not the same, there is an unequal distribution of electrons. Therefore, the molecule is polar. Letter C is a hydrocarbon chain. 1, 2, 3, 4, 5, 6. This molecule is known as hexane. We know that the carbon-hydrogen bonds in all directions are non-polar. We're learning to remember that. And because there's really nothing interesting on that chain, there's no halogen or functional group, it's just a straight chain hydrocarbon, it's also a non-polar molecule. Notice water we drew just a moment ago, H2O. I can see that it has 4 domains. 2 are bonded, 2 are unbonded, 4, 2, 2, giving you the molecular geometry that it's bent, and that's why you see it there with about a 104-degree bond angle. You stand in the center, and I look up and I look down, and I see 2 H's, but I also see this magnitude of a very rich electron cloud, making that a very polar molecule. An OH bond is polar, and water is polar as a structure. How are you doing? We just talked about this one a moment ago. We see that there's an equal distribution of pole on the carbon. Remember, it's 2, 2, 0, linear. Since the 2 domains are exactly the same, and they're being pulled evenly in both directions, it's a nonpolar molecule. However, the bond itself is polar because oxygen is far more electronegative than carbon. So I can draw this vector quantity, but overall the structure evenly distributes that pole to make a nonpolar molecule. And of course, 2 atoms that are identical have equal electronegativity, so nonpolar bonds, nonpolar molecule. It's great practice in kind of bringing forward some of the skills from Chapter 1 into Chapter 2. It says tetrachloroethene, ene. Now remember ene, that means a double bond. F means that there's 2 carbons. Tetra means 4. Chloro is chlorine. 4 chlorines on an ethene molecule. Tetrachloroethene. So, just to remind ourselves, this and this have both sp2 hybridization, right? 3 electron domains, making this trigonal planar. It says it overall does not have a dipole moment. Explain this fact based on the shape. This is a very polar bond on this carbon. This is a very polar bond on the carbon, heading out to the more electronegative chlorine. But do you see, based on the shape, that the electron pull away from those carbons are equal in all 4 directions? Therefore, the dipole moment would be 0 dibis. It is a nonpolar molecule due to the equal distribution. We have very polar bonds, but because they're distributing the charge evenly throughout the structure, it's a nonpolar molecule. Think symmetry to determine the polarity of a molecule. Sulfur dioxide has a dipole moment. Carbon dioxide does not. Based on the molecular structure, tell me why. So remember, carbon and sulfur each contribute a different number of electrons to the structure overall. So SO2 has 18 total electrons. Carbon dioxide has 16 total electrons. So let's take a peek. Put the least electronegative in the center, attach back the other atoms to the central atom, keep tally, fill the octet of everybody but the central atom. One, two, three, four, five, six. That used up 12. There are 2 left. Therefore, we place them on the central atom. That gives me no electrons left. However, we see sulfur is not finished in terms of an octet. So I'm going to take one set of the electrons from either oxygen and make a double bond. So those are gone. And I still notice, based on formal charge, sulfur has 1, 2, 3, 4, 5 assigned electrons, lives in group 6, so it has a +1 formal charge. Based on formal charge over here, we see that oxygen lives in group 6. It has 7 assigned electrons, so that's a -1 formal charge. Let's redraw and alleviate the formal charge, and you would do so by drawing double bonds in either direction. We still have the lone set on the sulfur, but by making a series of double bonds, we now have 0 for each of the atoms' formal charge. So this is the better structure because we got rid of the formal charge. Sulfur can expand its octet because it's in the 3rd period that has D sublevels. Now, is this polar? We have 3 domains. 2 are bonded, 1 is unbonded. 3, 2, 1 gives us a bent molecular structure. Keep in mind, the electrons up here give me a very rich region of electron charge. So that is indeed polar based on the fact we have a set of dots on top of sulfur. Now remember, carbon only donated 4. This structure, carbon dioxide, has 2 less dots. By the time we're done drawing this structure again, we end up with O double bond C, double bond O, but notice there are no spare electrons sitting on top of the carbon as we had for the sulfur. Therefore, 2, 2, 0 is its electron arrangement, 2 bonded, 0 unbonded, made this a linear structure, and therefore nonpolar. The electron pull is indeed even in all directions. So don't be fooled by just looking at a molecular structure. You have to dig deeper and build the molecule and decide, based on the number of domains, how many are equal in distribution and if they're unequal in distribution. Let's take a look at cis, 1,2-dichloroethene. Okay, let's stop there. Chloroethene, all right, ene, double bond. F means 2 carbons. I'm going to start with a carbon double bond carbon backbone. That's the ethene. On carbon number 1, there's a chloro. On carbon number 2, there's a chloro. And I wrote them in the same direction because I saw the word cis. There's cis, 1,2-dichloroethene. It has a very large dipole moment. That's telling me that it's very polar. Everything just erased. Whereas trans, 1,2-dichloroethene, that's trans, has a dipole moment equal to 0. So when I look at this distribution, they're telling me that this is polar and that this is nonpolar. So when we draw the structures, I can clearly see the electron distribution in the cis arrangement all being pulled to the top of the molecule, making the top of the molecule very electron rich and the bottom of the molecule electron deficient. In the trans configuration, I see the electron distribution heading down, and in the opposite but equal pull heading up. So they're being pulled in opposite directions equally, creating an overall equal distribution of charge, therefore a non-polar molecule. The dipole moments cancel in the trans, cancel one another, giving a net pole of 0. Cis are in the same direction, so the dipole moment is quite large. So the stereochemistry, the way that the atoms arrange themselves in the molecules, really do matter, especially with cis-trans on the double bond. So think about physical properties and reactivity. That presence of a polar bond strongly influences physical properties and the reactivity of molecules. Polar bonds are part of functional groups, the main focus of our chapter, defined as groups of atoms in a molecule that give rise to the function of that molecule. And by function, we mean how does it react with certain substrates? What is its boiling point? What is its melting point? Those are physical properties. This is all based on the polarity of the functional group. And what we'll soon learn is that those polarity, the interactions between charges, highly influences intermolecular forces or intermolecular attractions between the molecules. If you have two charged molecules in the presence of one another, opposite charges will interact and have a very strong intermolecular attraction. Nonpolar molecules, they're not attracted to one another. There's nothing of interest on the molecule, so therefore we'll see how they interact and influence their physical properties. So laying the foundation of a future lesson in the same chapter on IMF, intermolecular attractions, if you see a polar molecule, you're going to start suspecting things called dispersion forces. We're going to see something called hydrogen bonding. And there, of course, we're missing the dipole-dipole interaction as well. So I'm going to just kind of leave that there for a moment and say there's three what we call van der Waals forces. We'll have ion-ion interaction, but that's where this direction is heading, so we can predict qualities about those. So, I mean, just kind of thinking, how does polarity affect some of these physical properties? And we talked about the cis and the trans. Look at the melting points. Cis was a polar molecule. Trans was the non-polar molecule, and we can see how that affected the boiling point. It's going to take more energy to get a solution where the molecules cling to one another to overcome that and form a gas. It takes less energy to convince molecules that are not attracted to each other to let go and form a gas, and so forth. So that's the strategy we're about to take a little look here and decide how do these intermolecular attractions affect things like boiling points, melting points, and so forth. Here's a practice. Indicate the direction of the important bond moments in each of the following compounds, neglecting, of course, the nonpolar CH bonds. You should also give a direction to the net dipole moment. If no net dipole moment exists, state that the polarity is 0. So here we have a cis-ethene, difluoroethene. Remember that the carbon-carbon double bond. On this carbon is a hydrogen and a fluorine. That's how I'm drawing this picture. And it says cis. Cis means same direction. So I'll place the second carbon with its hydrogen and its fluorine on it as well. That is the cis configuration. We've determined that that's highly polar because the distribution is going in one direction only, making this an electron-rich and this area an electron-poor electron distribution. Therefore, this molecule is indeed polar. If we rearrange that configuration to show the trans, the dipole moments cancel one another. You would see a dipole moment being pulled in this direction. That's the vector quantity. You would see the dipole moment being pulled in the opposite direction. Equal but opposite cancel each other. Therefore, that's a nonpolar molecule. What if the carbon-to-carbon double bond showed fluorines on one side and hydrogens on the other? It's not cis or trans because I have two identical attachments on the same carbon, so it's impossible to say cis or trans. So I can clearly see this region of the molecule, that highly electronegative fluorine, would be very rich in electron density. So the vector quantity would simply be pulling towards that side. That's a polar molecule. If the carbon-to-carbon double bond had just fluorines, all directions were the same. There's a vector quantity in terms of distribution of charge, but it's equal and opposite in all directions. That's a totally symmetrical molecule, making the molecule nonpolar. That's going to conclude our lesson, and you've set yourself up now for functional groups, the heart of our chapter, functional groups, and that's going to be tackled in a group assignment of presentations. You will not have recorded lessons on the group presentations, but I'll pick up the recordings when those presentations are done, and we'll come back and look further at intermolecular attractions.